Welcome to the Embedded System course, Lecture 1, in which I shall try to introduce you to the concept of embedded system, and I shall also describe the ARM Cortex-M4 microcontroller and some of its interfaces. The main objective will be to learn to program one of the Texas Instruments TM4C series microcontroller for various mechatronic engineering applications. The microcontroller is TM4C123GH6PM, which is this chip shown here on the diagram. However, for the sake of application development, the microcontroller doesn't come alone. In fact, it comes with a complete package containing complementary electronics, such as the power management switches, the debugging interface, some displays in the form of LEDs, some switches, and large number of input-output port pins. And that's where we connect the external devices to be controlled and run by the microcontroller. And all of these things are integrated on the single PCB, and they are together called as the launch pad. We are going to use TM4C123G6L launchpad in your embedded system lab programming. Some examples of the input-output devices or peripherals that we wish to control by the microcontroller board include the keypad, LCD display, actuators such as DC motors, stepper motors, and sensor ICs, examples, humidity sensor, temperature sensor, pressure sensors. And we are going to establish an interface which allows microcontroller to be able to talk to these peripherals and to be able to run these peripherals the way we want them to be run. I'm going to conduct this course in a way that the description of the hardware and the software architecture for the embedded system, and I shall be talking more about that term in a bit, that doesn't require a deep architectural view of the microcontroller. In fact, I will try to focus more on the assembly language programming or the C language. And by means of that, we shall learn how to interface microcontroller with different I/O devices. Some of these we have already seen in the previous slide, such as the sensors, actuators, and the analog circuits. And the goal will be to understand how the real-world design proceeds, which often requires a careful analysis of performance versus cost trade-offs, and to better understand and describe our design within the constraints. One of them being the real time. And again, this will be described shortly. And in the lab, you will learn how to debug, test, verify, and validate your design so that you can know that if your embedded solution is going to work in real time. And note that there is no prerequisite for this course except the digital logic design, which you may have thoroughly learned in your first year courses or third semester courses. Following are the two textbooks, the Embedded System Introduction to the ARM Cortex-M Microcontroller 5th edition by Jonathan W. Volvano. The second book by the same author is also our textbook, but that is about the real-time interfacing to ARM Cortex-M microcontrollers. It's a 4th edition by Jonathan Volvano. The breakdown of the theory grade is follows. There are going to be 2 quizzes constituting 20% of the grade, 10% by each quiz. Midterm exam 30%, final exam 40%, and then there is going to be a course project, a single course project uh, whose one component will contribute to your theory grade, that will be about 10%. For the breakdown of your lab grade, please consult Mr. Shujat Ali for details. Alright, now let us try to understand embedded system and microcontroller in more detail. In order to understand what is an embedded system or a microcontroller, first need to describe what is a general purpose computer system so that we can contrast it with an embedded system or microcontroller. So remember, general purpose computer system is something that we are already familiar with, our desktop computers or laptops. And these are often equipped with the keyboard, disk, graphical display, and softwares, and you can download, modify softwares in a variety of ways. So in a sense, a general purpose computer system is not designed to run a specific application. In fact, it is a general purpose computing device capable of running a wide range of computer applications. By contrast, an embedded system is anything that uses a processor, but it's not a general purpose computer. So remember, a computer has a processor inside it. That's what we call the brain of the computer. So in this case, when we talk about the embedded computing system, it means that it uses a processor, but it's not a computer. In some sense, the user using the embedded system sees a special purpose system as opposed to a computer inside a system. So here we're talking about a special purpose in contrast with the general purpose system. And because it is a special purpose device, it doesn't have to run computational intensive operating systems such as Windows or Macintosh, although it may be running some variant, some knocked down version of these operating systems. And the embedded system must be user friendly. However, unlike the general purpose computer system, user cannot modify or upgrade the internals. The embedded systems are everywhere in our life, from cell phones to the automobiles, military applications, and again, they find a lot of industrial applications in the industry. So when we talk about embedded system, it is basically a microcontroller as the device that we wish to control by the microcontroller. That can be electrical, mechanical, chemical, or some optical device. So the device that is controlled and the microcontroller are combined in a single word, that is the embedded system. And inside the microcontroller, we see that we have a processor. It is the same processor that we find inside a computer system. But inside the microcontroller, we have something else, which is the RAM, random access memory, which is not found in the processor which is not found inside the processor of your computers. So the microcontroller has a processor which is doing the main computation, as well as the memory in the form of RAM and some memory in the form of read-only memory or ROM. And it also has large number of I/O ports so that it can communicate with the outside world. Again, this is a feature which is usually missing in the general purpose computing system. So an example of a microprocessor like Intel x86 series microprocessors, um, and you can name a lot of others such as ARM microprocessor, PowerPC, MIPS, etc. And microcontroller, as we have just described, it is not just a processor, it is a processor plus memory plus the input-output ports and interfaces. To summarize, a microcontroller contains a processor, memory, interfaces, and the I/O ports. So remember, processor is the basic processing component of the microcontroller, and in order to process the data, it needs some memory from where it can retrieve the data, process, and write back. And the memory can be volatile, such as the random access memory that we find in our computer systems, in which if the power is turned off, the data is lost. Or it can be non-volatile. A famous example is a flash memory, which is a type of EEPROM, the electrically erasable programmable read-only memory, that is capable of retaining data even if the power is turned off. So the memory sits very close to the processor in the microcontroller because the processor is constantly reading data from the memory, processing it and writing it back to the memory. And then we need to be able to connect the microcontroller with the real world. That's where these interfaces are very important. Interface will be described in more detail later in this lecture, but basically it has a hardware component, which is essentially the ports where the external devices are connected, and the software component contains the device driver, which are actually the functions or routines describing how the communication between the microcontroller and the device is going to take place. And finally, this I/O, input-output addressability, is also important. In some microcontroller, the addresses of the input-output devices are memory mapped, which means that if a microcontroller has to talk to the I/O device, then it is only going to write some data to the address that is in the memory. And remember, this is the same, in some sense, this might be the same memory that sits closely to the microcontroller. In other cases, we have a separate address space. That's where what we call is I/O mapped. In which case the processor has to separately remember these I/O devices addresses are not mapped to the memory, rather they have separate address space. An important attribute of an embedded system is its real-time operations, which means that we are putting an upper bound on the time required to perform the calculation and then to be able to respond an external event that is associated with the external device. But real time doesn't mean real fast. In fact, what we want from the real time attribute is that the time is short, and more importantly, it is bounded, so that we can know that our system, our embedded system, is going to generate the output that is in the form of a response to an external event in bounded time. So there are deadline guarantees that we seek in a real-time system. Now remember, our general purpose computer system, they are not real-time, even though they are trying to execute large number of instructions very fast, but there are no deadline guarantees. But because embedded system is running a specific task and it is trying to complete it in principle should be capable of completing the task within the deadline. So that's why the real-time attribute is a defining feature of the embedded system, hence the microcontroller. So it is not only is it necessary to get the correct answer, but it is also necessary to get the correct answer, that is the correct response from the microcontroller at the correct time. That's what the real-time systems do. Let us now take a quick look into ARM Cortex-M4 based microcontroller systems. So here is the basic processor of the microcontroller, and it is connected to several wires shown as buses. We call these wires a collection of wires as buses. For example, there is an instruction flash ROM containing the instructions. So these are all the instructions that the processor shall execute. And one of the interesting feature of this microcontroller system is that it has a Howard architecture, meaning that we have two separate buses carrying different parts of the instruction to microcontroller. For example, one section of the bus is known as the I-code bus, which is transmitting the op code, that is the exact code of the operation, telling microcontroller exactly what operation that it needs to perform. So that information is conveyed through the I-code bus, and the data, if it is a constant data that needs to be processed, that information is sent separately through a different part of the bus. We call that decode bus. And because the two buses, they are separate, so we can decode the instruction simultaneously with the acquisition of data. That feature is often useful when we wish to implement the pipeline processor, although that is not going to be this theme of our discussion in this course. Then there are other buses, the system bus that is connecting the microcontroller with the RAM. That's where the data will be temporarily stored, read from or written to. And the system bus is also connecting the input and the output ports. These are shown as separate blocks here, but physically they are just the same I/O ports that we described earlier. So note that the system bus is connecting the processor, RAM, and the port. So it is connecting three things. And one of the things that you should note about the speed of the bus is that more the number of connections, slower is the bus speed. That the data rate, the rate at which the data can be transferred on the bus, depends on the number of interconnection. Higher the number of interconnection, slower is the bus. The data rate is low. And they have another bus, the advanced high performance bus. That's a high speed bus. That is connecting microcontroller only with the input output ports. So there are some fast I/O operations which are needed. For example, when you want to read data from the external flash drive, that's where this high performance bus will be useful, and this bus is not connected to the RAM. So that is only connected the this processor and the I/O ports. And there is a private peripheral bus that is connecting the processor with some internal peripherals. These are basically the interrupt controller and system tech, which I shall describe at the end of our lecture. And what about the register and the memory map? What is a register? Well, registers define a tiny memory space that is inside the microprocessor. In the diagram shown here, there are as many as 16 registers. In reality, there are more than that. And all the registers have the same size in terms of the number of bits. There are two types of registers: the general purpose registers that are visible to the user for general purpose task or the arbitrary purpose, put in different words. And then there are special purpose registers which have a special role that can be utilized while writing the program, while programming the microprocessor. And again, these will be described and discussed in more detail in the future lectures. The memory map shows that the memory is divided, logically divided into 4 segments. A flash ROM containing the instruction and the instruction constants, within the instructions. The RAM that we saw in the previous slide, the addresses of the I/O ports, and then there is some portion of memory that is allocated to internal modules such as the timers, PWM, and the interrupt controller that's which are connected to the microprocessor through the private peripheral bus. A detailed architecture of the input-output ports as well as some of the internal modules is shown here in the diagram. As many as 6 general purpose I/O ports are available: A, B, C, D, E, and F. And although the pins on these ports, they can be programmed to play different roles. And that's because the ports, they are internally connected with the modules. For example, there are modules implementing the serial communication. When a microcontroller wants to serially communicate or send or receive data serially from an external device: YART, SSIs, CAN, and I2C interfaces. Similarly, other modules such as the timers, analog comparators, PWM, and analog to digital converters, they are also connected to the I/O ports, general purpose I/O ports. And exactly how to describe how to configure the role of each port pin, that remains a topic of our future lecture. Here again, the thing to notice is that there are 2 separate buses: the advanced peripheral bus that connects my controller with the ports as well as the internal modules, but that is a bit slow compared to the advanced high performance bus that connects microprocessor directly with external port pins. I/O pins can be configured either as input pins or the output pins. An example for an I/O port pin configuration circuit is shown here. The circuit contains 2 buffers controlled by separate control signals. At any one point, only one of the buffer is active. And remember, the role of the buffer is to just transmit the logical information from its input to the output. So for example, if we wish to configure the pin over here as the input pin, that is, the microcontroller wants to read data from the pin, then this will be the route. In this case, the upper buffer is activated and the lower buffer is deactivated. And the data that is read by the microcontroller can also be latched over here, but microcontroller can also latch new data into this flip-flop, the D flip-flop. And if a microcontroller wants to further write this data or route this data to the same port pin. Now in this case we want this port pin to be an output port, then this is going to be the route, in which case we have to activate the lower buffer, that is this one, by means of a control signal over here. And this control signal is first latched into the flip-flop, and this latching apparently seems synchronous with the data which was latched in the upper flip-flop. And because the read and the write operation needs to be synchronized properly by means of a clock, so therefore the control signal and the data, they are first latched to the corresponding flip-flops, and then they are dispatched. One of them is going to activate the buffer, and the second one is the input of the buffer, in which case when the buffer is activated, the input simply goes to the output, as in this case. The configuration requires changing some of the bits inside the GPIO port direction register, and this just requires binary information. 0 means input and 1 means the output. Again, this will be discussed in more details in our future lectures when we shall describe the programming scheme for the IO ports. So we've been talking about the interfaces. What exactly is the interface? Well, is a hardware and the software that combine to allow the computer to communicate with the external hardware. So remember, interface is a combination of hardware and the software, and it must be able to adapt a wide range of inputs and outputs that can exist in digital or digital, analog, or time forms. But this really, the first part, I think, is the most concrete definition of the interface. However, we need to see what are some of the examples of the interface modules that we saw in the port architecture diagram, that is in this diagram. So there was an interface implementing the serial communication in different ways. One of them being the UART, that is an acronym of Universal Asynchronous Receiver Transmitter. So UART is a 2-wire high-speed reliable serial communication interface, and it is suitable for constructing a network of microcontrollers, or if we want to connect microcontroller to PC for the firmware update or for debugging purposes. The SSI interface is the synchronous serial interface, or also known as SPI interface, the serial peripheral interface. It is actually a 4-wire medium speed serial communication interface that is suitable for controlling some interesting peripherals that we saw in the beginning of the lectures: the LCD, the ADC, and DAC, and some others. The I2C interface, also known as the inter-integrated circuit, is a 2-wire low-speed serial communication interface, and it is suitable for acquiring data from multiple sensors or a network of sensors. For example, if a microcontroller it needs to be interfaced with a variety of different sensors, then it can use the I2C interface to acquire data. And then we have another interface, the CAN, the Controller Area Network. There was a CAN module, remember, that we saw in the diagram. Again, it is a 2-wire serial communication interface equipped with error detection, pardon me, and therefore it offers it offers greater reliability along with the high speed. The CAN interface has been widely used in the automobile. That is where we wish to enable communication between different electronic control units, and each electronic control unit has a specific role to play, such as an ECU for the transmission system, or the steering system, or the light control system. And each ECU may be very different. These ECUs may be very different in their construction or functionality, but they can all be connected with the help of the CAN controller area network. And these are also used in several industrial automation modules. Now, apart from the interfaces, microcontroller also contains some internal modules. One of them was the nested vector interrupt controller, NVIC. So the keyword over here is the interrupt. So what is interrupt? Well, when some input-output device such as keyboard or keypad mouse seeks immediate service, what it does is that it requests my controller to pause its ongoing operation using an interrupt signal. So you need to interrupt my controller to grab its attention. That's what an I/O device does. And once the attention is grabbed, then the microcontroller is requested to execute a different function till the service is done. So, and then only after it has service the I/O device, it can resume its normal execution. So that's where the NVIC controller becomes handy. It helps microcontroller to manage and prioritize the interrupts and the execution of the interrupt service routine. That is the program that needs to be executed when the microcontroller gets interrupted by some I/O device. Timers, very similar to the digital counters that you study in your digital logic design course, and these are used to introduce specific delays or timing information. A simple example, that example where you can easily use timer, or where using in timer is much more intuitive, is the implementation of the alarm clock. And finally, we have the pulse width modulation module. What is PWM? So pulse width modulation, acronym PWM. It is actually a hardware that dynamically adjusts the duty cycle of the square wave, also known as the pulse width. Okay, so where it is useful, motor speed, position control, finds a lot of application in robotics and related areas of mechatronics. And pulse width modulation can also be used in the power line communication and several other examples that we don't have time to cover over here in more details. Alright, so this brings us to the end of our first lecture. It was an introductory lecture, and I hope to quickly give you an overview of the different internal components of the microcontroller that we are going to study and program in this semester. I hope you enjoyed listening to this lecture, and we are going to have a follow-up Q&A session on Thursday afternoon starting at 2 p.m. And at the end, I would like to give the credit, the slides credit. These slides that you have seen have been taken from the Jonathan Volvano website with his permission, and a lot of these slides have been modified according to the needs of a lecture. With that, I would like to formally conclude this lecture, and I wish you a good health, stay safe, and stay healthy. Thank you very much.